Welcome to this explainer. Okay, today we are looking at the absolute master builder of the natural world, carbon and its compounds. I mean, it's literally the architect of life itself. From the DNA twisting inside your cells to the fuel in your car, or even that diamond on a ring, carbon is the foundation of it all. So let's explore how just one single element can pull all of this off. Here's our roadmap for today. We're going to start by looking at carbon's crazy versatility, then we'll check out its covalent bonds and allotropes. After that, we'll break down the families of hydrocarbons, observe some chemical reactions, and finally, look at everyday carbon like the soap sitting right there in your bathroom. Section 1. Carbon, the versatile element. The foundation of living organisms, fuels, and diamonds. It's honestly mind-blowing that one single element is the core ingredient in everything from the food we eat, to the plastics we use, to the medicines that literally heal us. Okay, let's dive into this. Why does carbon form millions of different compounds? What makes it so incredibly special compared to, the rest of the periodic table? Well, the secret lies deep down in its atomic structure. The first big clue here is tetravalency. Carbon has exactly 4 electrons in its outermost shell, and to be perfectly stable, it needs 4 more to complete its octet, so it forms 4 covalent bonds. Imagine carbon as this tiny master builder with 4 hands, just constantly reaching out to grab onto other atoms. This makes it an absolute structural powerhouse. It perfectly bonds with, say, 4 hydrogen atoms to create methane. But here's the thing, carbon doesn't just hold hands with other elements, it absolutely loves to hold hands with itself. We call this property catenation. Carbon atoms join with each other to form straight chains, branched chains, or even these complex ring structures. Because of catenation, carbon builds endless variations. It can scale up from simple little molecules like ethane to massive looping structures like cyclohexane. It's basically molecular Lego. Moving on to Section 2. Covalent bonds and allotropes, sharing electrons to build different forms. Let's see exactly how carbon shares its electrons to build these completely different structures. In carbon's world, sharing is caring. Instead of aggressively gaining or losing electrons completely, carbon just shares them. This creates what we call a covalent bond. And the result of this sharing is actually pretty fascinating. Covalent compounds generally have low melting and boiling points, and they're really poor conductors of electricity. This is exactly why your basic carbon compounds, like methane or carbon dioxide, are usually just gases or liquids at room temperature. But when carbon atoms bond only to other carbon atoms, wow, things get wild. These different physical forms are called allotropes, and the contrast is extreme. You've got diamond, literally the hardest natural substance on Earth, where every single atom forms 4 rigid bonds. We use it in heavy-duty industrial cutting tools. Then you have graphite, made of the exact same atoms, but arranged in layers, so it's soft, slippery, and actually conducts electricity. Perfect for pencil leads. And then there are fullerenes, these incredible football-shaped molecules that researchers are using right now in cutting-edge nanotechnology and medicine. Same building block, totally different results. Section 3. Families of hydrocarbons, the structural blueprints of carbon compounds. Now that we've got the bonds down, let's look at how we categorize these complex blueprints. So, hydrocarbons are just compounds made entirely of carbon and hydrogen, and they fall into 2 main camps. First, we have saturated hydrocarbons, known as alkanes. These have only single bonds between the carbon atoms, like ethane. They are completely saturated with hydrogen, right? On the flip side, we have unsaturated hydrocarbons. These contain double bonds, which we call alkenes, or even triple bonds, called alkynes. And that simple change in the type of bond completely changes how the whole molecule behaves. And here is how these carbon compounds scale up through a homologous series, which is basically just a family of compounds with similar chemical properties. Methane is CH4. Ethane is C2H6, propane is C3H, butane is C4H10. Do you see the pattern there? Every single consecutive member simply tacks on an extra CH2 block. The fundamental chemistry stays similar, but the molecule just gets bigger and heavier as you go down the line. So what happens if we decide to swap out a hydrogen atom for something else entirely? Well, we get functional groups. Think of these as chemical add-ons that completely change a compound's identity. Slap an OH group on there and your hydrocarbon turns into an alcohol, like ethanol. Swap in a CHO group and it makes an aldehyde. A double-bonded oxygen gives you a ketone, and a COOH group creates a carboxylic acid. Okay, so why does any of this matter to you? Well, these tiny chemical add-ons dictate our everyday lives. That alcohol group, it gives us ethanol, which is absolutely crucial for the hand sanitizers we rely on, not to mention a bunch of medicines. What about that carboxylic acid group? It gives us ethanoic acid, which you probably know better as the vinegar sitting right there in your kitchen pantry. Seriously, just a few atoms swapped out, and you go from a flammable gas to a salad dressing. No way, right? All right, Section 4, Chemical Reactions and Properties. How carbon compounds interact and transform. Time to step into the lab and shift from static structures to dynamic action. The most famous carbon reaction is one you use every single day: combustion. When carbon compounds react with oxygen, they burn. This produces carbon dioxide, water, and, crucially, heat and light. Burning methane, for instance, is how we generate a massive amount of our energy. It's the primary fuel reaction that literally powers our modern world. Next up is oxidation. This is when a carbon compound essentially gains oxygen. For instance, an alcohol can undergo a chemical change to become an acid. You can take ethanol, that alcohol we just talked about, and oxidize it right into ethanoic acid. So yeah, literally, with a little oxidation, your alcohol transforms directly into household vinegar. Now, industry uses this exact kind of chemistry to alter our food through an addition reaction. You start with an unsaturated hydrocarbon, like liquid vegetable oil. By adding hydrogen and using a nickel catalyst to speed the whole thing up, those double bonds break open to accept the new hydrogen atoms, and the result? A saturated product. It turns liquid oil into solid fats, like Vanaspati ghee. It's a real game changer for food manufacturing. Finally, we have the substitution reaction. This happens in saturated hydrocarbons, like methane. If you expose methane to chlorine in the presence of sunlight, the sunlight actually provides the energy for the chlorine atoms to aggressively step in and just swap places with the hydrogen atoms. Hydrogen gets kicked out, chlorine substitutes in, and boom, you've just manufactured chloromethane. Section 5. Everyday carbon, soap and life. From chemical reactions to clean hands, let's bring this micro-level science back up to the macro-level world. Have you ever wondered how soap actually removes stubborn grease? Well, it is all thanks to this fascinating carbon structure called a micelle. A soap molecule basically has a split personality. It has a water-loving or hydrophilic head and an oil-loving hydrophobic tail made of a long carbon chain. When you wash your hands, those tails eagerly attach themselves to the grease, while the heads face outward toward the water. They form this microscopic sphere, the micelle, trapping the dirt inside so it can be completely washed away down the drain. But there's a catch. Traditional soap has a major Achilles heel: hard water. The minerals in hard water react with the soap, reducing its efficiency and leaving behind this scummy residue. And that's exactly where detergents come in. Detergents are essentially modified carbon compounds, designed to be the modern heavy lifters. They work effectively to clean your clothes, even in those tough, hard water environments where regular soap just fails. So, let's tie this whole thing together. The secrets to carbon's absolute versatility really come down to 3 structural pillars: tetravalency, giving it those 4 bonding hands; catenation, allowing it to chain together endlessly; and covalent bonding, letting it share electrons to form incredibly stable, diverse structures. These 3 properties are what make carbon the ultimate element for life, medicine, and modern technology. To sum up this explainer, I want to leave you with a powerful quote from our source material. From the food we eat to the fuel we use, carbon is everywhere. Understanding carbon helps us understand life itself. I really want that to sink in for a second. We aren't just studying some random chemical element on a chart. We are studying the literal foundation of our existence. Which leaves us with this final thought. We've seen how carbon builds everything from the hardest diamonds to the DNA in our cells, entirely dictated by how it bonds and shares electrons. With our growing mastery of nanotechnology and chemistry, since carbon builds practically everything, what revolutionary new materials will we construct with it next? Thanks for joining me on this explainer, and as always, keep questioning the world around you.